All right, so this video is going to pick up with these examples. I hope at this point you've already tried examples 1 and 2. I'm going to go over those pretty quickly, and it should follow along with what we've already talked about in the first video. We're going to use those rules. So if you've already tried this, you may have already gotten 15 from multiplying 5 and 3, and 12 from multiplying 6 and 2. That, however, is not my final answer because I still have to simplify if possible. So I need to look at the square root of 12 and think, what perfect squares can I divide into 12? Which ones are factors of 12? And the first one that comes to mind is 4. So I'm going to rewrite the square root of 12 as the square root of 4 times the square root of 3. I'll bring my 15 down. The square root of 4 evaluates to the integer 2, whole number 2 out of a radical. And then 15 times 2 would give me 30. So this would be a simplified version of that. This one needs to be rationalized, so I'm going to do that by multiplying by the square root of 2 on the top and bottom. On the top, I'll get 6 square root of 2. On the bottom, I'll get 5 square root of 4, which would simplify down to 5 times 2, which would simplify to 6 over 10. Now this can be simplified or reduced like a fraction. So that, if I divide both of these in half, would simplify down to 3 square root of 2 over 5. Now another thing you could have done was divide 6 by 2 here, and that would have taken you directly to that answer. But this would be our final answer here. All right, on these next 2 examples, these next 2 remind us we have to think back to how we add and subtract radicals, where the radicand must be the same. So right now, I am not able to just add up 48 and 75 because I'm adding these radicals. I have to have the same number under the radical in order to do that. So the only way I'm going to be able to achieve that is if I can potentially simplify this until the radicals match up. So if I think about my perfect squares, 1, 4, 9, 16, 25, etc. As I'm looking at those, I can think about, do any of these divide into 48? Well, 4 would, but is there anything larger? I'm going to pull out my calculator just so I can show you how I can test these. If I divide 48 by 25, for example, that gets me a decimal, so that does not divide evenly. But if I divide 48 by 16, that gets me an integer value. So that is going to be the one I want to choose. And the reason I'm going to choose 16 as opposed to 4 is because the 16 is larger. I want to get the largest perfect square factor out. So I'm going to rewrite this as the square root of 16 times the square root of 3. So 16 times 3 would equal 48, which would then equal 4 square root of 3. That's for this first part. For 75, I know right away 75 is divisible by 25. I check to see what I get. When I divide it by 25, I also get 3, which is handy here in this case. So I'm going to rewrite that as the square root of 25 times the square root of 3. That would simplify to 5 square root of 3. Now I can add up these 2 radical expressions because the radicals match. I add my 4 and 5, and I get 9 radical 3. Be my answer for that one. Looking over here, square root of 3 isn't going to simplify down any further since it can only be divided by 3 and 1. But 12 I could simplify. And I just realized I actually accidentally put the perfect square part in the back, but that's okay. I can redeem it. I know that's going to go to whole number 2, so I'm going to write this as 2 times the square root of 3. That, I'm always putting the integer piece up front. The 4 is going to come down, though. So 4 times 2 would get me 8 square root of 3. So then I'd have negative 4 square root of 3 plus 8 square root of 3, which would equal 4 square root of 3. All right, on this example here, you've got a binomial. You've got 2 terms multiplied by 2 other terms. This is one where I want you to think of this as either foiling or using the distributive property. So you're going to multiply your first pair. 4 times 5 would get you 20. Your outside pair, 4 times negative 2 radical 3. And remember here, you can multiply the outside numbers, the coefficients. So I get negative 8. But I don't multiply the 4 with the 3 because the 3 is in a radical, the 4 is not. So this would just be negative 8 radical 3. My inside pair gets distributed. Radical 3 times 5. I'm going to write this as 5 radical 3 with the coefficient up front. And again, I don't multiply the 5 with the 3 to get 15 because that's an outside number, a coefficient, as opposed to a number in a radical. And then finally, my lasts there. I don't have a coefficient here that's visible, so I can think of that as 1. So it would be negative 2 times the square root of 9. Well, the square root of 9 is just equal to the integer 3. So this would really just become negative 6 from negative 2 times 3. So then here, I can combine these. These are like radicals. So that would get me negative 3 radical 3. And then last but not least, these are now just whole number integers, no radicals on those. So I can combine those as well and get 14 minus 3 radical 3. And that would be my final answer. Now take note, I cannot subtract these because these are not like terms. This one has a radical, this one does not. So I cannot simplify this down to like, say, 11 radical 3. I would have to leave it at that spot. All right, at this point, I'd like you to try multiplying out number 6 on your own. I'll start that one in the next video, but see if you can try that one based on what we did in number 5.